Okay, all right. So the question that we have, is clinical significance the same thing as effect size, since effect size measures the quantity of magnitude? So that's not quite true, that they're the same. So effect size is how much impact the exposure has on the outcome. But clinical significance tells us whether that effect size is important enough for us to care. Okay, so let's take a look at the question in this poll. So the question says, from your analysis of the average waiting times at A and C, if you remember the last question that we saw, that's what this is referring to. You estimated that women in rural areas waited 10 minutes longer than women in urban areas. Let us close our eyes to the confidence interval for a minute, because we have not gone over that concept, right? But if you have women in rural areas are waiting 10 minutes longer than women in urban areas, but you are told that 20 minutes wait will be of concern. So if you think about it, the finding from your results, from your analysis, is 10 minutes. So that's the effect size is 10 minutes, okay? But 20 minutes is what you're told will be of concern. That's the threshold that has been set. The question is, where does that come from? It might be that comes from your expert understanding of what should matter. And in some cases, we already know, maybe from biological studies, that maybe 20 minutes is when the waiting time becomes much of a problem. And there are many situations where this might be. So for instance, let's take a look at anemia. So in anemia and hemoglobin, if you have a woman who has maybe the change, let's think about the change in hemoglobin concentration is greater than 1 milligrams per DL, for instance, then you might say that this is a large enough increase in hemoglobin concentration. And if a person has less than that, then maybe that's too small to have any meaningful biological effect. And you might be able to take other parameters as well, say maybe blood pressure. You might say that if you take a drug that reduces blood pressure by up to, let's say, 30 milligrams of mercury in the space of 1 month, right? Say if you have someone whose blood pressure was 150 milligrams of mercury hypertensive, and then you're able to reduce it to 120. So the effect size of that drug is 30 milligrams of mercury, right? It might be that from your analysis, you already know that anybody who has up to 30 milligrams of mercury reduction, there's an impact on organ damage that is preserved. So you're able to prevent them from having organ damage. That is the threshold that you care about. That's what you're trying to prevent. Okay, so you then compare that threshold that you care about to what you obtain. And if the value that you obtain, your effect size, is less than the threshold that you care about, then you say that your effect size is not clinically significant. So it might be that 10 minutes increase, when you compare it to those who did not get the intervention, 10 minutes is still that 10 minutes reduction in waiting time. When you compare it to the clinics that don't get the intervention, it might be that 10 minutes is statistically significant, because statistics compares numbers to numbers, right? It doesn't compare like numbers to real life situations, but we need to be able to bring real life situations to matter. And that's why we have the concept of clinical significance. And this is very important, like I've given a number of examples, but it's often very important to help us decide whether the results that we do find are important enough for us to care. Okay, so if there are any questions, I'll take them. Or is this clear enough?
I have a question.
Okay, please. Okay, please ask your question.
Okay. So regarding sampling, you talked about convenient sampling, random sampling, and a lot of things. So I want to say, for the convenient sampling now, does the measure of spread not cover for it? Like, since we could not get random sampling, measures of spread, that's probably if you're using a mean and a standard deviation plus or minus, does it not?
Yeah.
Does it not cover for it?
Regardless of the sampling that we do, right, we will be able to obtain the measures of spread. So if you'll be able to obtain the mean, the standard deviation, you can calculate it. But the question is whether it is the correct thing to do. The question is whether you're obtaining a truly valid result, and oftentimes, so this is the thing about statistics and research, right? There is what is the best to do, and there is what you can do given the resources that you have, right? So what is best to do is to do a random sampling where you can be sure that each person has an equal probability of being selected. Okay, but in many situations, you don't have that. And Dr. Mota explained, you don't have the opportunity to do a random sampling. And so you're stuck. And you're stuck with a convenient sampling. The important thing to do is that you have to clarify to the reader that what I'm doing here is not a random sampling. I'm using a convenient sampling because, for whatever reason, maybe because I don't have money to do a random sampling, or because there is the logistics are just impossible, right? But you should know for yourself, and you should make the reader understand that your estimates might not be valid. And that's the thing. So all the measures of spread that we talked about, they will not account for the fact that you have used a wrong sampling method. And that's why sampling is and that's why it's the first thing that we talked about as we started talking about inference, because it truly throws off your analysis. So one point that I want to make as far as the validity is concerned is that if you use other approaches like the cluster sampling, the systematic sampling, the other approach, the other sampling methods that we talked about in class, you might be able to approximate to some extent the random sampling. And in some cases, you can use statistical methods to sort of get at something that will be close enough to what you would have gotten using a random sampling approach. Okay. And in those cases, maybe the analysis that you will do might be okay. And you might not, right, it's still not a random sample, but it's as good as, it's close enough. Unlike a convenient sampling where it's really not random. And you have to bear that in mind for yourself, but you also have to specify to the reader that this is an issue. It doesn't approximate it. It's not the same thing. That's the challenge that you're stuck with. Long and winded response, but I hope it's clear.
Yeah. So my second question is, if our significance level is at 5%, that's the chance, that's the level of risk we are ready to take. So does it mean that our confidence interval is 95%?
Okay, so you want to talk about confidence interval. Okay, let's talk about
just a yes or no, because I don't know. We've not done confidence interval, and I'm kind of confused.
Yes, the answer is yes. Okay, so confidence interval, we estimate it from the p-value. Okay, and that's precisely what we do, is that if we decide that the alpha level is 5%, then the confidence interval is estimated from 1 minus alpha. And that's why we come up with the 0.95, which is actually 95%. Okay. Now, the confidence interval, it gives us an idea of a ballpark of a world where, like if you repeated the experiment many times, okay? If you repeat the experiment many times, what is the likelihood that the value that you will get will fall in between these two values? So what's the so you're basically doing an estimate such that 95% of the time, if you repeat the sampling many times, 95% of the time, your values will fall in between the upper and the lower confidence interval. Okay, so that's really the concept of confidence interval. We'll go into it in more detail as best as we can, in subsequent classes, and we will have to learn it anyway. This is just like an introductory view into it. And yes, to answer your question again, you obtain it from the p-value. If your alpha level, you obtain from the alpha level. If your alpha level is 0.05, then the 95% confidence interval that you will estimate is the confidence interval that you will estimate is 95%. If your alpha level is different from 0.05, again, it is 1 minus alpha that you use to get the confidence interval, and there is a bit of work to do in the back end, and we can show that to you if we do get to it.
All right, thank you very much.
You're welcome. So someone asked if we should, I think Dr. Motar is back, but I think, let me take this question. Someone asked someone asked that I go over the explanation of clinical and statistical significance using hemoglobin. Okay, so hemoglobin is a good example because a lot of clinicians, a lot of health workers engage with hemoglobin on a regular basis, right? And if you're a pregnant woman, let's look in the concept of pregnancy, because that's also a commonly understood environment for a lot of us. So when people become pregnant, many women start pregnancy with an okay hemoglobin level. So let's say a hemoglobin is 10. Okay. Now, by the time she goes from the beginning of pregnancy to say one or 2 months after, a hemoglobin might drop from 10 to, say, maybe by 1 point it might drop to 9. Okay. And the clinician might look at it and say that 1 gram per DL reduction is what we usually see in many people. So that 1 gram per DL reduction is not strange, okay? But some other woman might have had maybe a bleeding, or might have had maybe malaria or something that had caused her a hemoglobin level to drop. And when a hemoglobin level drops like that, it might drop by maybe 1.3 grams per DL, right? Now, assuming that one person was a group of people, and when you looked at it, the mean hemoglobin level that dropped among this group of people who had malaria, for instance, right? The mean reduction in hemoglobin was 1.3. So if you compare that mean hemoglobin to the 1 gram per DL that you sort of expect to see based on your understanding of the biology of anemia and pregnancy, right? You might say that, oh, this is not too strange. This is not a reduction in the effect that we're going to be worried about. That is the idea of clinical significance. Is this impact, is it huge enough for you to be concerned, or is it too small that, okay, whatever, it doesn't mean, so clinical significance gets at how large the effect is, should we care. Statistical significance gets at how correct the effect is based on if we had repeated the estimation many times. Okay, so they're fairly different things, but we use them we kind of use them to make decisions together. Dr. Yes. Are you back? Yeah. Okay.
Yeah. So I just wanted to say that, you see, if you don't have a clinically significant, if you don't have a statistically significant, and I'm using that very loosely. If you have a statistically significant result, it's hard to start talking about clinical significance, because statistical significance is about how much confidence do we actually have that whatever difference you say you have, that does even in fact exist in that population. That's not entirely accurate, but for the purpose of this conversation, I think it's practical enough. So by clinical significance, we're actually asking, well, yes, there's a significant, there's actually a difference, but then so what? So what?
Yeah.
What does this mean?
Yeah, so we have another question. Someone said, can you explain what power and beta means again, please, and how are they related to alpha?
So essentially power is, so let me start from beta. You see, beta is the chance that is how much is the chance that you would not discover the finding, even though there's a real finding to discover. You know, in a population, say, okay, with this experiment we're talking about, where you are really testing a new anti-hypertensive, and you're taking the blood pressure of people who are taking this drug and comparing to people who have not taken this drug, and you're saying, if you look at the, say there's actually a difference. Beta is the chance that you would, even though that difference exists, you would not find that difference because of your own procedures, because of the way you do your samples. You end up reaching the conclusion that actually there's no difference between people who have taken this drug and who have not taken this drug. That is what beta is. The chance that you are wrong, you are wrong by saying that there is no discovery to be made, when in fact there's a discovery to be made. When in fact, that's, in technical terms, that's failing to reject the null hypothesis. When in fact, you should have rejected the null hypothesis if you had really looked at the whole population very well. That's what beta is. Now, power is 1 minus beta. That's the probability that you would not make that error. In essence, the probability that you would actually find the difference if the difference were in fact there. So people, usually you want to maximize your power. I'm doing a study, I want 100%. I want to, if there's actually a difference, that this, if there's a chance that this drug is actually working, I want to be very, I really want to find that effect. I really want to find that difference. The thing is, you can't always, you know, because of cost, because of so many things, you often cannot have 100% confidence that you would actually find the difference if difference is there. So the amount of risk you are willing to bear in failing to make the discovery, even though there's a discovery to be made, is what beta essentially is. So it's different from power and from alpha, but the amount, your power is not just a function of your beta. It's also a function of your alpha. Alpha is a different thing. Alpha is really that how much of type 1 error you're willing to tolerate. Meaning that if, when there is actually no difference, say you've done this test, in actual fact, the drug is not working. The people who are having, the people who are taking the drug and people who are not taking the drug, they're actually having the same blood pressure. But then you go ahead and say, well, I found a difference. The drugs are, you look at your sample and you actually find a difference, when in fact there is no real difference in the population. The chance that that is going to happen is what we call, the chance that that is going to happen is what your p-value is. Now, before you do your experiment, you have to determine that how much of that risk am I willing to tolerate? How much of the risk of discovery, of declaring a discovery where there is actually none, how much of that risk am I willing to tolerate? That is what your alpha level is. You might say, well, let me just say that maybe if I'm 95% sure that if I find a finding, if I'm 95% sure that that finding truly exists, that's good enough, then your alpha will be 5%, because the risk you will tolerate, there's still a 5% risk that the discovery you're making does not in fact exist. It's just a false discovery. It's a false positive. So that's, that's what we call a type 1 error when you make a false positive. The amount of risk of making the type 1 error that you're willing to tolerate is what your alpha is. And that's why, when you actually compute your p-value, you compare it to that your alpha, meaning that is my p-value up to the amount of risk I wanted to tolerate? If it's not up to it, then I think that I would go with the fact that this finding I've found is not a type 1 error, it's a true finding. Now, your power, your actual power, that is the risk that you will not make it, you will not make a type 2 error. I mean, your actual power depends not just on your beta, it also depends, your alpha also shapes it. But how your alpha shapes it is not really, I mean, it's a complicated relationship. All I'd like you to know for the purpose of this course is that power is 1 minus beta, meaning that it is the opposite of making a false negative error, making an error of rejecting a finding, of saying that there's no difference when in fact there should be a difference, of failing to reject your null hypothesis when in fact you should have rejected it. That is what power is, 1 minus beta, where beta is, you know, that risk of making that type 2 error. But power, even though it's like the flip side of beta, there are other things that kind of shape how much of power you have. And that's what I'm saying, that your sample size factors into it. Your alpha kind of factors into it also. The effect size that actually exists in the population does in fact also factor into it.
Any final questions? Okay, I guess in the absence of questions, thank you very much, everyone. This has been an excellent class. Thanks for your patience. The inference is a challenging subject, you know, and we've gone through some of it, but it's really important to help us sort of understand whether what we are doing at all makes sense. And this is why, you know, you don't just jump at research without like knowing, you know, sampling properly, knowing what your p-value means, you know, knowing what statistical significance means versus clinical significance. Some of these issues are really critical to help us make the correct inferences to use in our studies and in our lives, you know, as well. You know, as you better understand inference itself, it helps your decision making as an individual beyond just the research as well. It helps you to see where you might be making flaws because of the way that you're seeing the data, you know, and yeah, so that's important to bear in mind. We will send out the recording today. If you feel like you need to go over it again, we'll share the recording today. We will share the unedited recording just as is, and then we will try to share a better recording later. So that's one. Please look out for emails. If you have not completed your homework and you would like to complete it today, please do so. People who don't complete their homework, we will have to sort of leave out of the announcements for the class and everything, and then maybe they might be able to watch recordings later after the class or something if we decide that we want to make it public, but we will have to kick you out of the class, because this allows us to, you know, like the larger the class, the more challenging just running it is. And then look at the kind of thing that happens today with the Zoom. Some of it is because we have a fairly large class, right? We're really grateful to all of you for staying on and for being engaging. Please reach out if you have any issues at any time. Thank you very much. See you next week.
Thank you. Have a great one, everyone.
Thank you, sir.
Thank you, sir. It's been a great time tonight.
You're very welcome. I mean, for some reason, you would need to log me out of this.
Or what?
Out of the Zoom. Can you? Okay. I think I figured out how to get out.
Okay. Yes, sir.
So we cannot post a list of those who have submitted their homework, unfortunately. You know, if you have submitted your homework, if you think you have submitted your homework, you should check in your Gmail, your email accounts, you know, and just make sure that you have received a notification. Google will send you a notification that you submitted. If you don't find a notification, then maybe you may not have. Okay. Thank you.